In this video, we discuss section 24, analytic functions. First, we have a definition. A function f of the complex variable z is analytic at a point z0. Analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. That means if we choose a point z0 in the complex plane, and suppose that f is analytic in some neighborhood of z0. Okay, suppose that f of z is analytic throughout this neighborhood for some neighborhood, then we can say that f is analytic at z0. Okay, if f is differentiable everywhere in this neighborhood of z0, then f is analytic at z0. So this is the definition of analytic function. Note that analytic functions are also called regular functions or holomorphic functions. Both terms used to denote analytic functions. So a function is said to be regular at z0 if that function has derivative at every point of some neighborhood of z0. Similarly, you can call this analytic function as holomorphic function as well. Also note that if f is analytic at a point z0, it must be analytic at each point in some neighborhood of z0. That means if you have f which is analytic at this point, then you can easily get that function to be differentiable at every point of this neighborhood. So if you consider any point here, if this is z0 and take any point z0 prime here, then you can easily find a neighborhood inside this the original neighborhood in which the function is analytic, the function is differentiable, or function has derivative inside this, because we have assumed that f is analytic and therefore it has a derivative. It has derivative at every point of this neighborhood. So in particular, it has derivative at every point of the small neighborhood. So we can say that f is analytic at z0 prime as well. So if once we got this f is analytic at some point z0, then there exists a neighborhood of z0 in which this f is analytic itself. Okay, first of all, we will get the differentiability at every point of that neighborhood. Consequently, we can say that f is analytic at every point of that neighborhood as well. Now we have analyticity in an open set. If we have an open set like this, then if in order to say that this f is analytic in an open set, then that f should be analytic at every point inside or every point of that set. Okay, so in order to say that if this is a omega which is an open set, then in order to say that f is analytic on omega, we choose an arbitrary point z0 from omega and show that this f is analytic at this point. That means f is analytic at every point of omega, then f is analytic on this omega. Okay, in the similar fashion, you can define analytic function on a closed set. That is, if f is analytic on a closed set, if it has derivative everywhere in an open set which contains this closed set. Okay, so next we can see the analyticity of closed set, analyticity of a function in closed set. In general, f is said to be analytic in a set S which is not open. Then if this f is analytic in an open set containing S. Okay, so if this S is closed or not, whether it is a non-open set, then f is said to be analytic in S that need not be open. If f is analytic in an open set containing S. Okay, then we can say that we will get the analyticity of f inside an arbitrary set. For example, f of z is equal to 1 by z is analytic at each non-zero point in the complex plane. We know that at the point z equal to 0, this function is not defined. then we can say that f is not continuous, consequently it is not differentiable at z equal to 0. Then but we can say that if we choose any set except which does not contain this 0, then we can say that this function f of z equal to 1 by z will be analytic except for this point. Okay, all the set which does not contain this origin. Okay, so this is an example for an analytic function which is analytic at every non-zero point. But if we consider f of z equal to mod z square, which is equal to x square plus y square, last day we have seen that the CR equation does not satisfy except x equal to 0 and y equal to 0. That means CR equations are nothing but here u of xy is equal to x square plus y square, and v of xy is equal to 0, because this can be written as this plus I times 0. So this is going to be the u of xy, and this is going to be v of xy. Then ux will get ux x to x, vy as 0, and uy as 2y, and vx is equal to 0. So the CR equation should be satisfied if and only if x equal to 0 and y equal to 0. That means z equal to 0. That means except origin, this function, the components of this function do not satisfy the CR equations. Therefore, this function never be differentiable at every non-zero points. Okay, never. That means if you consider f dash 0, the definition of f dash 0 is limit delta z tends to 0. This is the derivative of f at z equal to 0. Okay, f of 0 plus delta z minus f of 0 divided by delta z. This is the definition of derivative of f at z equal to 0. Now we will get this is limit z delta z tends to 0. F of 0 plus delta z is this is nothing but delta x square plus delta y square, because this is delta z whole more delta z square. Okay, and minus f of 0 is equal to 0 itself, and divided by, so this is going to be more delta z square, then divided by delta z. Then you can write this as limit delta z tends to 0 more delta z square. This is the definition of f of z divided by delta z. Now you can say that this is equal to more delta z can be written as delta z into delta z conjugate. So this limit becomes delta z tends to 0 delta z times delta z conjugate whole divided by delta z, because more delta z square can be replaced as delta z times delta z conjugate, because z conjugate is mod z square. So by cancelling these two, you will get this limit as 0. Therefore, derivative of this function f of z equal to mod z square at z equal to 0 is 0. That means for this function, derivative exists at x equal to 0. So if we consider the complex plane, then we can say that for this function it has a derivative at z equal to 0, but it doesn't have derivative at every non-zero points. So if we choose any neighborhood of 0, we can say that only this function is differentiable only at this point. Except this point, the function is not differentiable. Therefore, this f is not analytic at z equal to 0. In order to get this f to be analytic at z equal to 0, we should find at least one neighborhood in which the function is differentiable. But using the conditions of CR equations, we can say that this function never be differentiable in any neighborhood of z equal to 0. Okay, so the differentiability of this function is only at z equal to 0. So this function is not analytic even though this is differentiable at z equal to 0. Okay, so the differentiability and analyticity of a functions are entirely different quantity. So this example illustrate that this f of z is differentiable at z equals 0, but it is not analytic. It is not analytic at z equals 0. Okay, so this is an interesting remark, and please note this example. Next we have a definition: entire function, a function that is analytic at each point in the entire complex plane, that is entire complex finite plane, is called entire function. So if you will get the analyticity at each and every point of the complex plane, we will call that function as entire function. For example, polynomials are entire functions. There are several examples. Polynomials are all entire functions. Similarly, e raised to z is entire function, and trigonometric function sin z and cos z are also example for entire functions. Next we can see the definition of singular points. If a function fails to be analytic at z0 but is analytic at some point in every neighborhood of z0, then z0 is called the singular point. That is, for the singular point we need to verify two conditions. One condition is the function f should fail to be analytic at that point, and if we choose any neighborhood of z0, then there should exist some points at which this f is analytic. Okay, this f need not analytic at z0, but f should be analytic at some point of every neighborhood. Okay, so this is the definition of singular point. For example, if we consider f of z equal to 1 by z, then we can say that z equal to 0 is a singular point, because we know that if we consider the point 0, then the function is not analytic at z equal to 0. This function we already seen that this function is not analytic at z equal to 0, but if we choose any neighborhood of 0, then we will get some point of this neighborhood at which this f is analytic. Okay, so this is an example for z equal to 0 is an example for singular point of f of z equal to 1 by z. Whereas f of z is equal to mod z square, there is no, for this function there is no singular point. Okay, there is no singular points, because this function has a derivative only at z equal to 0. That means if we choose any neighborhood of 0, then we cannot find points in the neighborhood at which this f is analytic. So this is an example for a function which has a singular point, and this is an example for a function which does not have singular points.